Chapter 9, Odd Number Problems 9 through 15. Number 9, to evaluate the effect of a treatment, a sample is obtained from a population with a mean equal to 30, and the treatment is administered to the individuals in the sample. After treatment, the sample mean is found to equal 31.3 with a standard deviation of 3. Notice that we're using a sample standard deviation opposed to sum of squared deviations. This will allow us to illustrate the process of computing this estimated standard error of the mean using standard deviation opposed to variance. A says, if the sample consists of n equal to 16 individuals, are the data sufficient to conclude that the treatment has a significant effect using a two-tailed test with alpha equal to 0.05? So here we need to first set the parameters of our test, and that's going to include setting the critical t-value. So to do so, we're going to need to calculate our degrees of freedom, which is n minus 1. So n is equal to 16, so degrees of freedom will equal 16 minus 1, and that'll give us 15. Again, we're going to use alpha at 5%, and we're told to conduct a two-tailed test. So we're going to utilize our t-distribution to determine our critical t-value. In our t-distribution, we enter it using our degrees of freedom. For this example, our degrees of freedom was equal to 15. We're going to use the two-tailed tier at 5% and see where those two values intersect. So if we go down here, we find that our critical t is equal to 2.131. Okay, so we've determined that our critical t is equal to positive negative 2.131. In other words, we need a t-value, a t-statistic that's going to be greater than 2.131. Let's go ahead and diagram what our distribution of sample means will look like, and again identify that at minimum we're going to need a value that sets the parameters on our negative side or below the mean and above. Again, we're hoping to fall in the critical region, in the tails, in order to reject the null hypothesis. Okay, to determine that, we're going to continue with this problem. Ultimately, what we need to do is solve for t. I'm just going to write our t equation and we'll come back to it. So t is equal to our mean difference, our sample mean minus the mu, divided by the estimated standard error. We don't have the estimated standard error, so let's go ahead and calculate that. Our estimated standard error is equal to, we have two different equations, one utilizing variance and one utilizing standard deviation. We have standard deviation, so we're going to use that equation, standard deviation over the square root of n, which is very similar to the actual standard error, which we learned about in the previous chapter. So this would equal 3 over the square root of 16, because our sample size is equal to 16. So if we take in our calculators, 3 divided by the square root of 16, we get 0.75. Now we have what we need to calculate our t-value. So t is equal to our sample mean, 31.3, minus our population mean, which was equal to 30, divided by our estimated standard error, which in this case is 0.75. And if we enter this into our calculators, 31.3 minus 30 divided by 0.75, we get a t-statistic equal to 1.73. So given what our standard was, again, our mu here was equal to 30. So our value of 31, given this t-statistic, falls somewhere in here. And we would conclude what I like to show visually. This makes us sad as researchers because at this point we would conclude that we would fail to reject the null. Again, what we were trying to determine is if the sample mean of 31.3 was statistically and significantly different from the population mean of 30. Let's not lose sight of what the null would state. Mathematically, the notation would have stated that the mu treated would equal 30, and the research hypothesis would state that the mu treated would not equal 30. And in this case, our sample mean, which is a representation of the treated population, was equal to 31.3. Numerically speaking, we would agree that 31.3 does not equal 30, but statistically speaking, what we've just concluded based on our t-statistic is that 31.3 is equal to 30. Again, statistically speaking, because we failed to reject the null. Numerically speaking, we would not say that that's true, but statistically speaking, based on where that t-value resides in our distribution of sample means, we fail to reject the null hypothesis. Number 9b, what we're considering now is, would the hypothesis test differ if we increased n to 36? So let's see if the test is different, our conclusions are different if n is equal to 36. So of course our degrees of freedom are going to change. So degrees of freedom again is n minus 1. So in this case, degrees of freedom would equal 36 minus 1, and that's equal to 35. So we're going to find our critical t using our t distribution. Okay, so our degrees of freedom for the problem we're working on was equal to 35. And this is a good example to focus on because if we look at our degrees of freedom, we actually don't have a value of 35. It goes from 30, we're over here, 30 to 40. And when we're trying to determine which value to use, the rule of thumb is to go with the first off the closest value, but then to choose the lower degrees of freedom. Because the relationship between degrees of freedom and a critical t is that as degrees of freedom increase, the t decreases. And you want to be as conservative as possible, so you want to go with the lower degree of freedom so that you end up with a higher critical t value. So let's just consider if I were to use degrees of freedom equal to 30, my t is equal to 2.042. If I go with degrees of freedom equal to 40, my t is equal to 2.021. And so when I say the more conservative t, I'm going to go with the t value that is further out in the tail. So this one would be further out in the tail, making the test more difficult to pass. We're splitting hairs. The values aren't that significantly different from one another, but nonetheless, as a researcher, you want to be more conservative. So the rule of thumb is to go with the degree of freedom that's lower. That's going to produce the higher t value. So again, we're going to use the 2.042 for this particular example. Okay, so as we found in our table, our t-statistic is equal to positive negative 2.042. And we're going to draw that out so that we get a sense of what we're working with. Again, the mean is 30, and we have these set parameters now at negative 2.042 and positive 2.042. We're going to calculate our t-statistic to see if we fall in the preferred critical region of our distribution. So we're going to calculate our t-statistic, which is m minus mu, the mean difference, divided by our estimated standard error. We're going to need to calculate our standard error. We have our standard deviation. Our standard deviation is equal to 3. So let's write our equation first. Standard deviation divided by the square root of n, and that's equal to 3 over the square root of 36, which would then be 3 over 6. And so in our calculators, 3 over 6, and we should get 0.5. So our t equation would then equal 31.1 minus 30 divided by 0.5. So in our calculators, if we take 31.1 minus 30 divided by 0.5, we get a t-statistic. Let's do that again. 31.3. I was getting something different, and now I know why. This is 31.3, excuse me. 31.3 minus 30 divided by 0.5, and we get a t-statistic of 2.6. So now let's go over to our distribution, and again, I can't stress enough how important it is to draw this out, because then visually you get a sense of the conclusions you're going to draw. So a t-statistic of 2.6 puts us well into the critical region, and as I visually like to show, we as researchers would be happy, because that means we get to reject the null. Again, the notation, the null says that the treated mu would equal 30. The research hypothesis would state that the treated mu would not equal 30. And now, statistically speaking, we've concluded that based on a sample of 36, we've pushed our t-value well out into the critical region, enabling us to reject the null and support this idea that the treated population mean is not equal to the untreated population mean. And that brings us to this last question, C, comparing your answers from parts A and B, how does the size of the sample influence the outcomes? We've talked about this relationship in the last chapter, and we've recognized that as n increases, variability, and in this chapter it's denoted by the estimated standard error, decreases, and in this case our t increases. And when our t increases, then our sample values are pushed further out into the tails, enabling us to reject the null. So large t values, or I should say larger samples, increase likelihood or probability of rejecting the null. Again, this is why we learned about Cohen's d in the previous chapter. We recognize that our interest lies in the mean difference. So we calculate Cohen's d as a measurement of the mean difference more so than the taking into consideration the effects of sample size. So here we see the difference in our conclusions given a change, or specifically an increase in sample size. Number 11, the spotlight effect refers to overestimating the extent to which others notice your appearance or behavior, especially when you commit a faux pas. Effectively, you feel as if you are suddenly standing in a spotlight with everyone looking. In one demonstration of this phenomenon, researchers asked college students to put a Barry Manilow t-shirt that fellow students had previously judged to be embarrassing. The participants were then led into a room with which other students were already participating in an experiment. After a few minutes, the participant was led back out of the room and was allowed to remove the shirt. Later, each participant was asked to estimate how many people in the room had noticed the shirt. The individuals who were in the room were also asked whether they noticed the shirt. In the study, the participants significantly overstated the actual number of people who had noticed. In a similar study using a sample of 9 participants, the individuals who wore the shirt produced an average estimate of 6.4 with SS equal to 162. The average who said they noticed was 3.1. Is the estimate from the participant significantly different from the actual number? Test the null hypothesis that the true mean is equal to 3.1 using a two-tailed test with alpha equal to 0.05. So our null is saying that those who were asked to estimate how many noticed them is equal to 3.1. The research is saying that their estimate is actually going to differ from 3.1. And we need to determine what our degrees of freedom are to find our critical t-value. So degrees of freedom is equal to n minus 1. Degrees of freedom in this case will be 9 minus 1, which is equal to 8. So we're going to find our critical t using degrees of freedom equal to 8. Okay, in our t distribution, we use degrees of freedom of 8. The second tier here at 5%, we're going to see where those values intersect. And we find that our t is equal to 2.306. So critical t is equal to positive and negative 2.3306. We're going to draw this out so we have our set parameters. So we expect that those who are wearing the shirt are going to estimate 3.1 individuals noticing them. That's what the null states, and our parameters for the test, our t values are negative 2.306, positive 2.306, and again, we hope that our t values fall in the critical region. To determine that, we're going to calculate our t value. So t is equal to m minus mu divided by our estimated standard error. In this case, we're given SS, so we're going to use that to calculate our variance. Variance is equal to SS over n minus 1, 162 over 8. If we enter that in our calculators, 162 divided by 8 gives us 20.25. We're going to now use that to calculate our estimated standard error, which is equal to the square root of our variance. Let me write the equation. The square root of our variance over n. So the square root of 20.25 over 9. So if we enter that into our calculators, you should have 20.25 in your calculator. Divide by 9 and take the square root, and we get 1.5. We can use that in our t equation. So our sample mean was equal to 6.4 minus our actual number of average number of individuals that noticed was 3.1 divided by our estimated standard error of 1.5. So in our calculator, 6.4 minus 3.1 divided by 1.5 gives us a t statistic of 2.2, and we're going to use that to look at our distribution and see where that falls. And in this case, unfortunately, it falls in this region. And that region tells us that, again, visually, I like to show, it makes us sad because we're going to fail to reject the null. And what that means in this particular case is, again, we were trying to determine if the estimate from the participants significantly differed from the actual number. And here we've concluded, based on these statistics, that the estimate or the average was not statistically significantly different. So we failed to reject the null. The estimate from the participants did not significantly differ from the actual number or average. Here, even though this problem doesn't ask for it, but it's a good point to introduce the final notation, your concluding statement. We identify that we conducted a t-test with degrees of freedom equal to 8. Our t-statistic was equal to 2.2, followed by a probability statement. When we fail to reject, the probability is greater than our alpha. And what we're saying is that this t-statistic of 2.2 fell into this region, this red region, right, the larger area. So the probability of obtaining a value of 2.2 is greater than alpha because it falls into that larger proportion or area of the distribution. So again, whenever you see fail to reject, then you should see this notation here. Those go hand in hand. So we say the probability of that t-value is greater than alpha, and at that point we are done with this particular problem. We didn't calculate any supporting statistics. Continuing with this same problem, now we've changed the parameters of the test by doing the following. Is the estimate from the participant significantly higher than the actual number? Mu equal to 3.1, just as a reminder of what we were working with. And again, mu was equal to 6.4. Now we're going to conduct a one-tail test, still at 5%, but this is how it's different from the previous example. We're conducting a one-tail test and still at 5%. And now what we're saying in terms of our hypothesis is that we anticipate that the individuals are going to overestimate what the actual number is in terms of those who notice them. So the research and the null. When we're doing a one-tailed hypothesis, it's often easier to state with the research. So we anticipate that the participants are going to overestimate or expect something higher, greater than 3.1. And the null is going to say the opposite and equal to. So they're going to anticipate that the participants are going to estimate that something that's less than or equal to 3.1. And given that we're conducting a one-tailed test, that's going to change our degrees of, well, our critical degrees of freedom isn't going to change because we're still using n minus 1. We're still using 9 minus 1 is equal to 8. But our critical t will be different. So we're going to use our t distribution to determine what that new critical t is equal to. Okay, So we're going to enter using degrees of freedom equal to 8. Now we're going to use this top tier. It's the first example of using a one-tailed test, 5%. So we're going to go over and see where those values intersect. And we find that they intersect at 1.860. So critical T, and it's important to indicate that we're going to focus on one value, the positive version of our critical T, positive 1.860, because again, we're anticipating that it's going to be greater than versus just a difference, as in the case of a two-tailed test. So let's draw this out. We have here in the center 3.1. We anticipate that we're going to produce a T statistic that is greater, hopefully greater than 1.860. Again, we're hoping we're going to be in the critical region. To determine that, we're going to calculate our T statistic. So to do so, we're going to, our T is equal to M minus mu over SM. None of these values have changed. All that we changed in this item in B is that we implemented the parameters of a one-tailed test. Everything else remained the same. So our T is still equal to 6.4 minus 3.1 over 1.5. So our T statistic is still 2.2. And given that value, now we check to see where that resides when we've applied a one-tailed test, and lo and behold, we see that it falls in the critical region. As we've indicated before, and from our reading, we know that a one-tailed test is easier to pass. We learned that in Chapter 8 because the critical values are set closer to the center of the distribution of sample means. And in this case, we would conclude that we get to reject the null and conclude that the estimate from the participants was significantly higher than the actual number. And the reason for the difference is, again, recognizing that when you have a two-tailed test, that alpha percentage or proportion needs to be split amongst two tails. When we have a one-tailed test, that proportion is allocated to one tail. And again, that critical value is pushed closer to the center of the distribution. So higher than the actual number, we conducted a t-test with T degrees of freedom equal to 8. Our T statistic was equal to 2.2. Something to note here that will be introduced in a subsequent chapter, but might as well introduce it now. When we conduct a one-tailed test, you want to identify that. And the reason, obviously, is that we recognize a one-tailed test is easier to pass, so you want to disclose that to the consumers of your research. Again, this will be introduced in a later chapter, but I'd like to introduce it now so we become accustomed to that notation. And then our probability statement, now we get to say the probability of obtaining that T statistic of 2.2 is less than our alpha 0.05, which again was what we were hoping for and makes us happy as researchers. Number 13, standardized measures seem to indicate that the average level of anxiety has increased gradually over the past 50 years. In the 1950s, the average score on the Child Manifest Anxiety Scale was mu equal to 15.1. A sample of 16 of today's children produces a mean score of M equal to 23.3, which is a sad statement of our society, with SS equal to 240. I see this with students all the time, that anxiety levels of students is on the rise, unfortunately. And so here's some data that maybe some of you can relate to, and support the things that, the changes that we see in the demands of individuals that result in emotional impact that we see. So we have present day values denoted in a sample in comparison to historical data of the 1950s. So what I want to do before we move on is just simply write out what the research and null hypothesis is, because we're going to conduct a test of significance. Well, let me read A. Based on the sample, has there been a significant change in the average level of anxiety since the 1950s? Use a two-tailed test with alpha equal to 0.01. So the null is going to state that the levels of anxiety have not changed since 1950. And the notation would be that mu is equal to 15.1. And mu, I just want to point out that this would be current day levels, right? And this is 1950 levels. I'm just going to clean this up a little bit. Whoops. Now I made a bigger mess. All right, so this would look like that. Levels, mu. So notice again, it's not a treated population. This is an example of a quasi-independent variable because it's the change in time before and after. So before 1950 and now current day levels of anxiety. The hypothesis would say that the levels of anxiety have changed since 1950. And we would say the current level does not equal the 1950 level average of 15.1. So we've established what the research and null hypothesis would look like. Again, we're going to test the null hypothesis using a two-tailed test at alpha equal to 0.01. So let's figure out what our critical T is equal to. Our degrees of freedom will equal n minus 1. And our sample size is equal to 16. So degrees of freedom will equal 16 minus 1. We're going to identify critical T. And again, we're using two-tailed test with alpha equal to 0.01. Okay, so we enter our T distribution using degrees of freedom of 15. We're going to use the second tier at 0.01 and see where those values intersect. And so we get 2.947. So our critical T is equal to positive negative 2.497. Now we're going to calculate our statistics to test for significance. So our T is equal to m minus mu over our estimated standard error. We need to calculate our standard error. Our standard error is equal to our, in this case, before I do that, I just noticed that we have SS, so we don't have variance yet, so let's do that first. So we have our SS, sum of squared deviations. So variance would equal SS over n minus 1. Variance would equal 240 over n minus 1, which in this case would equal 15. So in our calculators, 240 divided by 15. 240 divided by 15 gives us 16. Now with that value, we can calculate our estimated standard error, which is equal to the square root of our variance over n. We have 16 over our sample size, which is equal to 16, and so we get a standard error equal to square root of 1, which is equal to 1. Now we can calculate our t-value. Our sample mean is equal to 23.3 minus the population mean of 15.1 over 1. Now we can calculate that t-statistic. Looks like it's going to be quite large, so 23.3 minus 15.1 divided by 1, and wow, we get a very large t-statistic. And I neglected to set my parameters. I apologize for that. It's usually pretty telling once we have our diagram visual to rely on. So we set our parameters, and our t-statistics were quite high. It looked like we had a pretty hard test to pass given our alpha of 0.01. Nonetheless, we passed it with flying colors. It's again a sad statement of our anxiety levels, our current anxiety levels. So again, we look at this t-value and see that it resides way over here. And because we passed the test, again, we hope to fall in the critical T. I apologize for not doing all of these basics before. Because it falls well into the critical region, I put a happy face, but again, it's a sad statement of our society, of the trends of levels of anxiety, the changes that we have seen. Nonetheless, this is the test that we conducted, and the fact that we've found a very significant t-value shows that we have very high anxiety levels. The good news is that when we show significance, that often leads to changes, that we can address problems in our society given these types of results. So at this point, what we can now do is draw our conclusions. But before we do that, I'm actually going to hold off on that because we have a part B and part C for this particular item, and then we'll end with our concluding statement. Okay, so continuing with number 13, standardized measures seem to indicate that the average level of anxiety has increased. So we've just determined that that is statistically true given the t-value we calculated. Now in B13B, we're asked to construct a 90% confidence interval. So this is a new concept being demonstrated in these problems. A confidence interval is a range of values that estimates the unknown population mean. So given the parameters of the confidence, we are in this case saying that we're 90% confident that the true population mean resides within these values. So we're going to calculate that range of values. So our equation for calculating the confidence interval is the following. So mu is equal to the sample mean plus or minus our t-value, which I'll explain in a second, multiplied by our estimated standard error. Okay, so this is our equation. Now, we know our sample mean, and that was a given in the problem. So we can replace that variable. So mu is equal to 23.3. and then plus or minus, and this is a bit of a warning. This t-value is not the t-statistic that we just calculated. This t-value is coming from our t-table, and it is in relation to the percentage of confidence that we have determined. So we're going to use our t-distribution, and what we want to look up is given this range. So we are saying that we're going to solve for m here and m here using 23.3 as the center. So if we're able to reject the null hypothesis, and this is a good point to make, that you would not calculate a confidence interval if you fail to reject the null. If you reject the null, then you can calculate a confidence interval, meaning that you're going to estimate a range of what the actual population mu equals or would reside within. And we would use the sample mean as the basis for that calculation. In other words, if we reject the null, then this is a good representation of what we would anticipate the current day anxiety levels to equal, 23.3. But we're going to recognize that it's a sample, and that the true population mean is somewhere close to that. And so we're going to calculate that range. So that 90% is here. So within this 90% confidence interval, or 90% of the time, that anxiety level score is going to fall within this value to this value. And so what that means is what's left over is 10%. 10%. And so to find this t-value in the equation, we're going to convert that 10% to a proportion. So 10 divided by 100, and that gives us 0.10. And whenever we're calculating confidence interval, it's always the process of a two-tailed structure, because again, we're calculating sample values on both sides of the mean. So one value here and one value here. So we're going to use this value in our t-distribution and the two-tailed tier to find out what this t-value equals, in addition to our degrees of freedom. So that's another value we need. Our degrees of freedom is equal to 15, because n is equal to 16. Okay, so the things that we need is, again, we're calculating 90% confidence interval. So what we need to, again, recognize it's 90% in the middle, leaving 10% in the tails, so 10% in the tails distributed over two tails. But again, we turn that 10% into a proportion, just a review of what I just did. And again, the confidence interval calculation is always in relation to the two-tailed process. So we're going to look for 0.10, and that's here. And then we're going to enter using our degrees of freedom of 15. So we're going to see where those intersect. And we get a value of 1.753. So again, that's how we find our t-value to calculate our confidence interval. So we just found our t-statistic equal to 1.753. And our standard error has not changed. It's still based on what we calculated in the previous example. It's still equal to 1. Now we're going to have, again, it's positive negative here, which means, again, we're calculating two different means above and below a value of 23.3. So let's do the high end first. So essentially we're taking 23.3 and adding, since we're multiplying by 1, adding 1.753, and we get a value of 25.053. So I'm going to clean this up a little bit so we see what we're doing. So again, based on our sample, if we were able to reject the null, the sample mean of 23.3 gives us a good sense of current day anxiety levels. It's a good representation of the population. And now we're going to calculate a range of values that occur 90% of the time in the population. And the first value we came up with was 20, I'm going to write it here, 25.035. And on the low end, again, because we're multiplying by 1, 23.3 minus 1.753, and we get 21.547. So if I'm just going to give myself a little more room here. So a range of from 21.547 through 25.035. All right, so technically what we've determined, the confidence interval says that if we were to estimate today's population mean of anxiety, 90% of the time that level would range between 21.547 to 25.035. Another way of thinking about it is if I took a sample of today's population, that their average, a sample of 16 individuals from today's population, their average level of anxiety would fall within this range 90% of the time. Again, it's based on the sample, right, that proved to be statistically significant. That's the kind of the default and a good representation of the, in some cases, treated population, but in this case, the current day anxiety levels, given the fact that this value was statistically significant. So we're 90% confident that today's population anxiety level ranges between 21.547 to 25.035 based on the sample mean of 23.3. Okay, so based on what we concluded in the last part, our results would be as follows. So we're going to write our concluding statement. So we would reject the null, which stated that current day anxiety levels are equal to those of 1950. We reject that idea. The results indicate that anxiety levels actually, I'm going to backtrack a little bit here. So I'm going to write that current day anxiety levels are significantly different than levels of the 1950s. And again, we'll follow up with our statistics of the type of test that we conducted. We conducted a t-test, degrees of freedom equal to 15. Our t-statistic was equal to a whopping 8.2. Our probability was less than 0.01. Again, the probability of obtaining a t-statistic of 8.2 was less than 0.01. I'm just going to clean that up a little bit. It looks kind of messy. All of it looks messy, I know. 0.01. And then we would write, in this case, our supporting statistic would be our confidence interval. So we're 90% confident, our confidence interval. And we write that in brackets, would be 21.547, comma, 25.053 brackets and then period. So again, that's telling the consumer of our research that yes, we were successful in our test, and we're 90% confident given this sample statistic of 23.3 that the expected population anxiety levels would fall within this range 90% of the time. Number 15, for several years, researchers have noticed that there appears to be a regular year-by-year increase in the average IQ for the general population. This phenomenon is called the Flynn effect after the researcher who reported it, and it means that psychologists must continually update IQ tests to keep the population mean at 100. To evaluate the size of the effect, a researcher obtained a 10-year-old IQ test that was standardized to produce a mean IQ of 100 with a population 10 years ago. The test was then given to a sample of 64 of today's 20-year-old adults. The average score for the sample was 107, with a standard deviation equal to 12. Based on the sample, is the average IQ for today's population significantly different from the average 10 years ago, when the test would have produced a mean of 110? Use a two-tailed test with alpha equal to 0.01. So let's begin with our null in our research hypothesis. So our null says that the IQ for today's population does not differ from the average IQ 10 years ago. And therefore, the notation would be the mu, and again, that refers to current IQ scores. The average of the current IQ scores would be equal to 100 based on the average. Again, that's the average IQ 10 years ago. Again, normally we wouldn't see 10 years ago, we wouldn't see all of this extra information. You would simply just see mu is equal to 100, but I like to differentiate what we're looking at so that you understand what we're comparing. So the mu of the current IQ would equal the mu of the IQ 10 years ago. The research hypothesis would say that the IQ for today's population is significantly different than the average IQ of 10 excuse me, of 10 years ago. And the notation would be that mu, right, again, the current IQ does not equal 100. All right, and we were given some statistics, or the sample statistics. Again, we're working with a sample equal to 64 that generated a sample mean of 107. We're going to convert that into a t-statistic to determine if it's statistically significantly different from 100. We know numerically it is. To do so, we're going to need to set the parameters of our test. We're going to need to identify what the degrees of freedom are equal to. Degrees of freedom are equal to n minus 1. Degrees of freedom in this case would equal 64 minus 1, which would give us 63. And then we, using this information, two-tailed test at alpha at 0.01, we're going to identify our critical t-value using our t-table. So we're going to utilize our t-table to identify this information. Okay, so in our degrees of freedom column, we're going to enter using 63. We don't have a value of 63, and again, as I indicated before, the rule of thumb is use the value closest to and actually go lower. Our choices are 60 or 120. We're going to go with 60, and again, go with the lower value that yields a higher critical t-value. We're going to use a two-tailed here at 0.01. We're going to see where those values intersect. So come down here and we come up with a critical t of 2.660. So we've identified that our critical t is 2.660, and it's plus or minus since it's a two-tailed test. Let's draw our distribution. So we identify where our values reside that partition the critical region. So we have negative 2.660 and positive 2.660. Again, we're hoping we fall into the critical region based on our t statistic that we're going to calculate. So to calculate our t-value, our t is equal to the mean difference divided by the estimated standard error. We're going to need to calculate our estimated standard error. In this example, we're given our standard deviation, so we use that equation. So our standard error is equal to our standard deviation over the square root of n. So standard error, estimated standard error is equal to 12 over the square root of 64. So in our calculators, if we enter 12 divided by the square root of 64, we get 1.5. So now we can calculate our t statistic. Our t is equal to our sample mean of 107 minus our previous average IQ average of 100 divided by our estimated standard error of 1.5, and we get a whopping t statistic again in our calculators, 107 minus 100 divided by 1.5, and we get, if we round 2 digits right of the decimal, 4.67. So again, using that value to place it on our distribution, we see that it's well into the critical region. Again, we are happy as researchers given the evidence we need to reject the null hypothesis. So at this point, again, we know that we're going to reject the null based on the fact that our critical t-value fell into the critical region. It was well beyond a critical t of 2.660. And the next problem is going to ask us to calculate a confidence interval and then write our concluding statement. Okay, continuing with item 15, B says let's construct a 80% confidence interval of today's population IQ. So if we were to estimate what today's population IQ would be using the old test, given the test score of 107, which was the sample mean, let's predict with 80% confidence what the range of the actual population mean would be using the old test. So our confidence interval is calculated using the equation mu is equal to sample mean plus or minus t multiplied by our estimated standard error. Again, we're using the sample mean as the basis of our calculation. Again, that's the default. It's a good representation of what we'd anticipate today's population average to equal if we applied that old test to the entire population. So we're going to calculate, again, a range of values, right? So 80% of the time we'll get a value here all the way to a value here. These are the two m's that we're going to calculate. And in the center, it's all based on this average of 107, which came from the test sample that produced an average of 107. The values that we know are 107, and we're going to calculate we're going to locate our t-value. Again, it's not the t-statistic that we just calculated. Don't make that error of entering your t-statistic. It's a t-value derived from our t-distribution, and we'll look that up in just a second. Our estimated standard error is still the same of 1.5. So in order to find our t-value, we're going to take into consideration that we're calculating 80% confidence interval. So what's left over is 20%. 20%. We're going to use that 20% to find our t-value. So if we convert 20 into a proportion, we get 0.2000, and we're going to use that in a two-tailed process along with our degrees of freedom, in this case 63, to identify t. Because again, the confidence interval calculation is a two-tailed process. We want to find out what the values are on either side of that sample mean of 107. So let's utilize our t-distribution to find that value. Okay, so again, as illustrated, we're talking about 80% in the middle, 20% in the tails. It gave us a proportion of 0.2. And again, we're talking about the two-tailed tier, so we're going to focus here in this tier. We're looking for 0.2, and that would put us here. Degrees of freedom for this problem was equal to 63. We don't have 63. We're going to use 60, so that places us here. And we're going to see where those two things intersect, and it would be here. So we're talking about a t equal to 1.296. 1.296. Okay, so we've just concluded that our t is equal to 1.296. So now we enter that into our equation, 1.296. And now we can solve for our estimated population mean, the range. So I'm going to erase some of these things to make room for my values. So in our calculators, if you will, again, we're going to have a value below the mean and above the mean. So the value above the mean, given 1.296 multiplied by 1.5 added to 107, we get a value equal to 108.94 on the high end. And then if we take 1.296 negative multiplied by 1.5 added to 107, we get 105.06 if we round. So again, we're talking about a range of 105.06 through 108.94. And just to make this more appropriate, I'm just going to do a comma here because these are the two values. Again, because we're doing plus and minus, or the negative and positive version of this product here, we're going to get two different values. So essentially what we've just calculated is that we're 80% confident that if we were to use the old the 10-year-old IQ test, today's population IQ average would range from 105.06 to 108.94. That's what we just calculated. And now we can draw our conclusions. Before we do that, I'm actually going to calculate Cohen's d because we haven't seen that yet. So estimated d is equal to m minus mu over s. And that would equal 107 minus 100 divided by 12, and that gives us 0.58, and that's considered a medium effect given the table in chapter 8. And now we can draw our conclusion. So the results, so first we reject the null based on our t-value. The results indicate that IQ scores have significantly changed in the past 10 years. We conducted a t-test with degrees of freedom equal to 63. Our t-statistic was equal to 4.67. Our probability statement would be that the probability of obtaining a t-statistic of 4.67 is less than 0.01, or alpha. We can include our supporting statistics of D. D is equal to 0.58. This wasn't asked in this problem, but it was a good thing to include as an additional supporting statistic. And then our confidence interval. So we calculate 80% confidence interval. So we're 80% confident that if we were to administer this 10-year-old version of this test, the population IQ average would range from 105.06 through 108.94. And that's it. That would be our concluding statement for this particular research example.